Welcome. So, we would like to develop the analog of Fourier series on the finite group, what we are looking at Z n, and towards this what we have observed, one of the fundamental properties to deal with the Fourier series is basically e to the power I n theta, which are orthonormal, and then they are nothing but a homomorphism from the identified with the periodicity of the 0 to 2 pi to mod 1 complex number, and in fact it is a continuous homomorphism. So, to do the Fourier analysis, in the last lecture we have defined the function phi n of j. This is equal to e to the power 2 pi I j n over n. So, where n varies over 0 to n minus 1. Then what we have observed is that with the inner product on the space of all functions on Z n, we had defined and we found that phi k, phi j, this is equal to 1 by n if k is equal to j and 0 otherwise. So, now if this is if I take a phi k, this by our notation, this is equal to norm of phi k square, this is equal to 1 over n. This will imply that phi k 1 by square root of n. Oh, sorry, there is a slight mistake, which is equal to I get n, and then this is n, and this is square root of n. Now, if we normalize this, let us call it as E star of j is equal to 1 over square root of n phi j, then one can see that proposition E j star is an orthonormal basis for V, and this is of course what we have now. What we need to show is the proof is obviously now E j star E k star, which is equal to 1 over n phi j phi k, and this is equal to 1 if k is equal to j and 0 otherwise. So, therefore, this is an orthonormal. Now, in order to do to see that this is a basis, of course, we are 0 to n minus of 1. The moment we show that they are linearly independent, then they are going to be a basis, because we have already seen that V has dimension n, capital N. Therefore, here linearly n linearly independent, they will form the basis. Now, so towards this end, let 0 is equal to summation over j from 0 to n minus of 1 alpha j E j star. Then what we want to show that alpha j's are 0, that is trivial. So, because if we take the summation over j from 0 to n minus 1 alpha j E j star, and I take the inner product with E k star, then this what I am going to get is summation j from 0 to n minus of 1 alpha j E j star E k star, and that is if This will only survive if j is equal to k, and that is going to give us 1. So, therefore, this is alpha k, and this is definitely 0, because 0 with the inner product with anything is 0. So, alpha k is 0, this is for each k, hence E j star j from 0 to n minus of 1 are linearly independent. Okay, so that means they are the orthonormal basis for this. So, now the most two important result in the Fourier series what we have seen, they are inversion formula and the Parseval identity. Now, so now towards that let us recall, if f is from Z n to C, define f k to be 1 over n summation over n from 0 to n minus of 1 f of n e to the power minus 2 pi I k n by n. This is the Fourier transform, Fourier coefficient of f what we had defined. So, now if I look at f inner product of E j star, then this is going to be 1 over, this is summation over n from 0 to n minus 1 f n E j star n bar. This is equal to 1 by square root of summation over n from 0 to n minus 1 f n e to the power minus 2 pi I j n by n. Okay. So, now this one is nothing but square root of n f of j. So, with this observation, let us write down the inversion let f be a function from Z n to C, then 1 is that f of n, this is equal to summation over k from 0 to n minus of 1 f of k e to the power 2 pi I k n by n. And then the second thing is that which one would like to have, the Parseval identity. This is nothing but the inversion f k square, this is equal to 1 by n f of n square. Okay. So, this is nothing but the Parseval identity. So, we can collect all the observation what we have observed over here. So, So, now proof f belongs to V, this implies that f is equal to summation over j from 0 to n minus of 1 alpha j e j star, because they are orthonormal basis. So, I can express this. Now, what about this alpha j? So, this alpha j is going to be nothing but, if I take the inner product with that alpha. Okay. So, now if I take the f inner product of E k star, then this is going to be summation over j from 0 to n minus of 1 alpha j E j star E k star, this is equal to alpha k. So, therefore, f is equal to summation over j from 0 to n minus of 1 inner product of f E j star and E j star. Now, earlier what we have calculated that the inner product of f E j star is nothing but summation over j from 0 to n minus of 1 square root of n f j, and then E j star. E j star I can write it as 1 by square root of n e to the power 2 pi I j this is E j star f of n, I will write this is as n. So, this is j n by n. So, now square root of n goes out. So, what you get is that j equal to 0 to n minus of 1 capital F j e to the power 2 pi I j n by n. Okay. So, that is what we have got is the inversion formula. Now, for the Parseval identity for the proof of 2. So, if I take n from 0 to n minus of 1 mod of capital F n square. So, this is equal to, by our earlier calculation, is going to be 1 by n summation over n equal to 0 to n minus 1 f E n star mod square, because 1 by square root of n, that is what we have got. So, now this. So, this is equal to 1 over n summation over n equal to 0 to n minus of 1 and mod of summation over j is equal to 0 to n minus of 1, and because I am going to write the inner product. So, this is going to be f of j E j star E n star mod square. Again, the orthogonality orthonormality of E j star, this is going to give that this inner sum, this is going to survive only when j is equal to n, otherwise this is going to be 0. So, therefore, this is n is equal to 0 to n minus of 1 mod of f of n square, and that is what is our Parseval identity. Okay. So, now we are all set to do the Fourier series, because we have the most important results in the finite group, particular finite group Z n. Okay. So, then one can have a corollary. Let g of n is equal to f 1 of n into f 2 of n, where f1, f2, g, this all these are mapped from Zn to C. Then the Fourier coefficient of this g, we denote it by capital G, g of k, this is equal to, if the Fourier coefficient of f1 is capital F1, convolution of f2, which is the Fourier coefficient of small f2, this is at k. This is the proof. Let us just write down g of k. This is equal to 1 by n summation over j is equal to 0 to n minus of 1 g of j e to the power 2 pi I minus 2 pi I j k divided by n. Now, we will plug in the value of g. J k by n. Now, we have the inversion formula with us. So, this will tell that this is n minus of 1. If I am writing the inversion formula, here this is going to be L is equal to 0 to n minus 1 f 1 of L e to the power 2 pi I L j by n, then f 2 of j e to the power minus 2 pi I j k by n. This 1 by n, if I take the sum L sum out, n minus 1 f 1 of L to summation over j from 0 to n minus of 1 f 2 of j and e to the power uh, 2 minus of 2 pi I, this is j, if I take common, then this is k minus of L divided by n, and this is nothing but with the factor of 1 by n, this becomes the Fourier transform, Fourier coefficient of small f 2. So, this is L equal to 0 to n minus of 1 f 1 of L f 2 of k minus of L, and that is what is our definition of the convolution. So, also what we have seen earlier is that let f be the Fourier coefficient of f 1 convolution of f 2 and f 1 and f 2 Fourier coefficient of f 1 and f 2 respectively. Then f of k, this is equal to f 1 of k into f 2 of k. This we have seen, and so now other way around also, because of the inversion formula just now we have seen is that if the Fourier, if the function is the product of two function, then their Fourier coefficient, they are nothing but the convolution. Okay. So, now let us do suppose I have a function, let us for example, I have a function f from Z 2 to C, and G from Z4 to C. Then what is going to be the relationship between the Fourier coefficient of G vis-a-vis F? So, does there exist? And now this I need to define it. Suppose if G of this is Z4 is equal to 0, 1, 2, 3 and this is equal to 0 and 1. Now, if I define my G of 0, this is equal to f of 0, G of 1, this is equal to 0, G of 2, this is equal to f of 1 and G of 3, this is equal to 0. Then what is going to be the relationship? Can we find between G and F? Okay, so in general, what we can ask for is that let if we want to ask this question for any arbitrary n and n, then let capital M is the product of two non-negative integer, two natural number, and my f, I am taking a function from z n by m to c, that means m prime to c. Now, we define this in this way. If I want to define G of n, this is equal to f of n by m if n is equal to 0 plus or minus m plus or minus 2m, whatever. Remember that if m, 2m, 3m, so this is divisible by m, and now so obviously I can go suppose 4 or 5, then Z4, then 5 is going to correspond, 4 is going to correspond to 0, 5 is going to correspond to 1, so on and so forth. So, I can define for all n like this, because it is going to fall back with the sum modulo, and then 0 otherwise. Then the question is that compute G in terms of the Fourier coefficient of f. And this is what we are going to derive in the next lecture. Thank you.